So a key piece of information for chemical engineers is exactly how much energy can be derived from combusting a fuel. What is the energy that's available to us that we can harness to make use of in some mechanical form? So we need to think of combustion of a hydrocarbon as happening in 3 steps. So step 1, we need to decompose that hydrocarbon fuel into its carbon and hydrogen atoms. Then the combustion reaction is going to form carbon dioxide and it's going to form water. And in that process, there's going to be some energy released. So the difference between what it takes to break down that carbon fuel versus what energy is released when those combustion reaction products, the carbon dioxide and the water, are formed, is the heat that we want to trap. And so we can see this here is described as the heating value. So heating value is the energy that's contained in the fuel minus the energy of the products of combustion. And so for us, our primary focus will be on transport fuels, but we'll look at some different options as well. But transport fuels can generally be modeled by isooctane. You'll notice at the gas station there's the different grades of fuel, so they are for different octane ratings. The more octane there is in the gasoline, the more efficiently it will burn. But of course you have to pay a higher price for that higher efficiency fuel. And then of course there's diesel, if you have a diesel vehicle, modeled by cetane. So most fuels have pretty similar heating value outputs. There's a little bit of a difference between them, but it's a good kind of rule of thumb to use 45,500 kilojoules per kilogram of fuel as the average heating value, regardless of the specific transportation fuel that we're talking about. So let's take hexane for example. So we have a kilogram of hexane. We're going to assume that it produces approximately 45,500 kilojoules of energy. So we want to know how much carbon dioxide is released in obtaining a kilojoule of energy from the combustion of hexane in the air. So that means we need to balance the reaction that we see in front of us. So we've got the hexane combined with the air. Of course, it's going to only react with the oxygen. The nitrogen passes through, as we saw in those air-to-fuel ratios notes. And so we're going to produce carbon dioxide and water plus the nitrogen pass through. So we've got to balance this stoichiometric equation as our first order of business. So on the left-hand side for the carbon, we can see we've got A times 6, so 6A. And then on the right-hand side, we just have C atoms of carbon. For the hydrogen equation, we've got 14 times A. And then on the right-hand side, we've got 2 times D. For the oxygen, so it's O2 inside times the B out here, so we get 2B equals, now oxygen is present in both the carbon dioxide and the water, so it's going to be 2C plus D. And then for the nitrogen, since that's just the pass-through, we can just do 3.76 times B equals E. So solving that system of equations, we can start with A equals 1, and we're just going to assume a value since we have more variables than equations. So if we say that A equals 1, 6 times 1 equals C, so that means we've got C equals 6. So then if A equals 1, so 14 equals 2D, so that means D equals 7. Then we jump down to the 2B equation, so we've got 2B is equal to 2 times C, so 2 times 6 is 12. Plus 7 for D is going to be 19. So that means B is going to end up being a fraction here. 19 divided by 2 is 19 halves. And then I'm not even going to bother with E until I actually have the correct value for B, since it doesn't interact with anything else in the equation. So I'm going to multiply everything by 2. So that means we've got A equals 2, C equals 12, D equals 14, B equals 19, and then if I plug in 19 for B to figure out what E is, I'm going to get 71.4. So I can slide those into my balanced equation. So I've got 2 moles of the hexane plus, then we got B is 19, so 19 times the mole of oxygen plus the 3.76 of nitrogen yields, and then for the carbon dioxide we've got 12 moles of carbon dioxide plus D was 14, so 14 moles of water, and then plus the 71.4 moles of the nitrogen gas. So now that we have that balanced equation, let's go back and take a look to see what we need to find in the problem. So I've kind of cleaned things up here. But if you'll recall, we want to know how much carbon dioxide in kilograms is released per kilojoule of energy. So that means the units on our final answer that we want to end up with are kilograms of carbon dioxide per kilojoule. So that's our end result. And we're going to start from the 45,500 kilojoules of energy per kilogram of hexane. So we want to make the conversion from the known amount of energy per kilogram of hexane to the number of kilograms per kilojoule of the carbon dioxide. So we're going to start with this, but we're going to flip it upside down because we want to end up with kilojoules in the denominator. So the only way we're going to do that is if we start with 1 kilogram of the hexane, so C6H14, per 45,500 kilojoules of energy. So this gets us started with our kilojoules on the bottom where we want them to end up in our final answer. And so now it's going to be a series of conversions that get us from the kilograms of the hexane to the kilograms of the carbon dioxide in the numerator. So my first order of business, so that I can make use of my balanced equation, is to convert the kilograms of hexane to moles of hexane. So we have 1 kilomole of the hexane over its molar mass, which 12 times the 6 carbons plus 14 hydrogens gives us 86 kilograms of the hexane. So we can include that there. Now I need to convert from moles of hexane to moles of carbon dioxide. So we can see that our relationship is 2 to 12. So I'm going to put the 12 kilomoles of carbon dioxide on the top and the 2 kilomoles of the hexane on the bottom. And then my last conversion is going to be to switch from moles of carbon dioxide to kilograms. And so my relationship there is just going to be the molar mass. So 1 kilomole of carbon dioxide, and so 12 times, 1 carbon, so 12 plus the 32 for the oxygen, so it gives us 44 kilograms of carbon dioxide per kilomole. And so now this is just a multiplication and division question. We're going to push buttons on our calculator. And so we eventually end up with a result of 5.08 times 10 to the negative 5th kilograms of carbon dioxide released per kilojoule of energy when you're burning hexane.